Hello, in today's class we are going to do some ladder programming exercises using Unity Pro XL software for Schneider PLCs. The first task we are going to work on is to program the NAND, or in other words, NOT AND function. Before we move on to programming, let's just go ahead and have a look at what a NAND or NOT AND function is and what it does. If we have two inputs and one output, these two inputs can take four different states, them being 0, 0, 0, 1, 1, 0, and 1, 1. And when both inputs are 1, the output is going to be 0, and in all other cases the output is going to be 1. And the logical expression for the NOT AND gate or NAND gate is going to be AB's complement. So whenever A and B is giving us 0, which is the first three cases, our output is 1, which is the complement of it. Now let's go ahead and program this logical gate using Unity Pro XL. The first thing we need to remember is that we need to run the software as administrator. We say yes, and then we wait for the software. So in here we are going to have two inputs and one output. When the software opens up, what we will need to do will be to define those inputs and outputs. Well, in this case, the two inputs and one output, and then to program the NOT AND logical gate. Here I have the complete project, but whenever we start a project from scratch, the first thing we need to make sure is to register what kind of hardware we have, what kind of CPU we have, what kind of input and output cards we have, and in which slots they are located. So this is the configuration we have up in the lab, and it is the same configuration we'll be using throughout the course whenever we use Unity Pro XL in here. So we have our CPU unit, we have our digital input card, we have our digital output card, we have our analog input card and analog output card. And the remaining of the slots are empty, but it means we can expand our PLC by use of additional components in here. So there are two ways to register our inputs and outputs. One of them is using the elementary variables in here. under variables and FP instances folder, if we can remember them. Or the way that I would suggest, especially in the beginning stage, is that we go ahead and use the graphical interface we have in here, and then define our inputs and outputs. So now we are going to work with a digital input. We are going to work with two digital inputs, A and B, as shown in here. So we have two inputs and they are digital inputs, meaning that they can take the value of 1 or 0. So the part that we are interested in using is this digital input card in here. So what we do is that we go over it and then we double click, and we are in here. We click on I/O objects, and we want to create two inputs. So you'll go ahead and select I in here and then say update grid, and then it's going to list all the inputs that are available in our system. I'm going to go ahead and use the first two inputs in here. So we have the address of the input in here, and then we have the name. So the first input, which is A, I named it input 0, and then the second input, which is input B, I named it input underscore 1, and the type is eBool. The difference between bool and eBool is that when we have a Boolean type variable, we are not able to force it in the system, but when we have an eBool type of variable or eBool type of contact, then we are able to force it to the state we wish. So in here, if I was creating a new one, another one, I would come and click on the name of the input that I have, or the address of the input that I have, and then name it, then say create. I am also able to write a comment in here, which is helpful in remembering what the variable is used for. Well, I only need two inputs, so I'm not going to create another one in here. I will leave it the way it is. So I'll go back to my graphical interface in here. I've created my two inputs, which are A and B, in my case input 0 and input 1. Now I need to create an output. That's also going to be of digital type because it can take only the values of 1 or 0. So I'll go ahead and click on the digital output card in here, and this time I choose % symbol and Q in here because that is the symbol for output. I say update grid, and then all the outputs are listed for me. I'm gonna go ahead and take the very first one in here, and I'm going to name it output 0. And then that's going to be of type eBool again, for the reasons that we have talked about. So I have three variables, two input and one output. I can go ahead and click on the elementary variables section in here and check what I have and modify them if necessary. I have input 0, input 1 and output 0 in here. They're all of type eBool, and then I have the addresses in here, So let's go ahead and change the input 0 to A, input 1 to B. When the software is asking for confirmation for the changes, I say yes, and the output, let's go ahead and show it by Q. So now we have A, B as inputs and Q as output. So what I need to do now is to start my program. Under the program section, I go to mask and sections, and then I right click and I can say new section. In here I'm able to use different programming languages or different programming methods, but in here I'm going to go ahead and use letter, so I'll choose LD, and I'll give my program a name. In this case I've given the name NAND in here. So let's go ahead and double click on the program and see what it does. So I have A in here, B in here, and then I have Q in here as my output. So if I go ahead and have a look at my gate in here, whenever one of them is 0, or whenever both of them are 0, then my output is 1. But when both of them are 1, then my output is 0. So I have A as normally closed and B as normally closed as well, and they are connected to my output. So when A is 0, my output is 1. B is 0, my output is 1. A and B are both zeros, my output is again 1. But when both of them are 1, then my output is going to be 0. So after I have built my program, I can go ahead and build it. I say yes. And we are waiting for the software to be built. And if everything is okay, we are going to get 0 errors and 0 warnings as it is in here. So it looks like everything is okay. And I'll say connect. And I need to make sure now I download the project onto the PLC, so I just click on download and I say transfer, yes. So if you guys paid attention before I have done the downloading of the program, in here I had a red message saying that it was different. The program that was on the PLC was different from the program that was on my screen in here. But now that I've downloaded it onto the PLC, they are equal, and I have the screen equal sign in here. If I want to run a simulation, I go ahead and say run in here. So when we first started, as both of them are going to be 0, A and B, then my output is going to be 1. Let's go ahead and force, right click on A and then force it to 1. I can see that it is still 1. So now let's go ahead and do the same for B. I force it to 1, but my output is still 1. But if I can force both of them to 1, then my output is no longer active as it's shown in here, which corresponds to the final case in here. So that is how we can tackle the first exercise in here. So now let's go ahead and talk about the second exercise we have, which is to program XOR or exclusive OR function. What is the truth table for XOR or exclusive OR function? Exclusive OR function let's go ahead and have 2 inputs again, here as before. So A and B are my inputs and Q is my output. They can take 4 different values in here. So they can both be 0, A can be 0, B can be 1, A can be 1, B can be 0, and then they both can be 1. So in an XOR gate, whenever we have both of them 0, we are going to have 0. Whenever one of them is 1, we are going to have 1. And when both of them are 1, we are going to have 0 again. So for XOR, my Q is going to be given by these 2 cases, which is 0, 1 and 1, 0, which correspond to A prime B plus A B prime. So this is what I should program for this exclusive OR gate. A prime B plus A B prime. So I opened the program, I made some changes. In here we have 2 inputs and 1 output. So I use input underscore 0 and input underscore 1 as the names for the variables, and I use output underscore 0 as the output in here. And I've changed the name of my later program so it's meaningful for the function that I'm going to program. So I'll have A B prime, so A B prime plus, which is the OR. So in one branch I have A B prime, on the other branch I have A prime B, and then they are connected to each other, and these 4 inputs are connected to the output in here. So let's go ahead and see how this works. Okay, I need to build it first. So I get no errors and no warnings, but in here it says it's the program on the PLC is different from the program that we have in here. So what we are going to do is that we are going to download it onto the PLC. So now they are equal, but it's not running. So I'll say run. So when we first start, both of them are 0, and my output is 0. So I'll go ahead and force input 0 to be 1, and then my output has become 1. I'll go ahead and say force to 0. And now what I'll do is that I'm going to go ahead and force input 2 to be 1, which is in here. And in this case, again, my output is green, meaning that it is active. But what if I go ahead and say both of them are going to be 1? Then my output is no longer active. So it's important that we start with some truth table, and then we translate it into a program, and we run some simulation and compare it to what we have expected our program to behave. Then we can move on to trying it on the actual hardware. So that was what we had for the second exercise. So let's continue with the third exercise. We are supposed to program this function into the PLC. A, B, plus C prime plus D. So we need to have A and B in AND action. Then A and B is going to be connected to C prime with OR action. And then we will have another OR action, and we will have the input D connected to it. And this entire entity is going to give us the output for our program. So A and B are going to be in AND. So in this case I have defined 4 inputs: A, B, C, and D. Input 0, input 1, input 2, and input 3. And 1 output here. So A and B are going to be in AND action. So A and B are in AND action. Then we are going to have C prime, which is in here, and that's going to be connected to A times B with OR. And finally we are going to have D, and that's going to be connected to all of these with OR. So we have this in here, and then we have the output. What about the fourth exercise? The fourth exercise is going to be an oscillator, meaning that we are going to have an input that goes on and off, on and off. So it has a continuous cycle of going between on and off by itself. So how can we make a program that's going to do that? I'm going to go ahead and open it. Our program is going to have only 1 input and 1 output. So we have our output relay, and then we have another relay in here. When our output is 0 in here, since we have the complement of it, this is going to be forced to, the output is going to be forced to 1. And when it goes 1, then this is going to be 0, then the output will be 0. When the output is 0, then this will turn into 1, and then the output will go to 1 again. And the cycle will keep repeating itself. Let's go ahead and see how this happens. I'll first build it. Luckily no errors, no warnings. So we say connect. Okay, and now we download it into the PLC. And we say run. So as we can see in here, the output keeps alternating, keeps oscillating between on and off states by itself. So this is how we can program a simple oscillator. What about the fourth exercise in here? The fourth exercise is asking us to program a one-shot function. And we need to program it in the beginning of our ladder program. So one shot is an output that is on only for one cycle or one scan time, and then it remains off the remaining of the program runtime. We can program something like this in two different ways. One of them is using an internal relay, just like we have done with the oscillator. And another way is to use an external input signal, an input signal from an external device. So let's look at the first way of doing it by using an internal relay. So in this case we need to have two outputs and two internal relays in here. When the program first starts, all of the outputs, meaning that output 1 and output 2, are going to be 0. And this internal relay, which is output 2's complement, is going to be 1, and therefore output 1 is going to be 1. And then the program, since our ladder program will go from top to the bottom, after the first line is executed, the second line will be executed. Output 1 is going to be 1, and output 2 is still 0. So output 1 is going to make output 2 1 as well. And then in the remaining of the program we are going to have some different rungs, and they'll be executed. And after one scan time has been completed, our program will go back to the beginning, but this time output 2 is 1. So output 1 is going to turn into 0. And output 1 is going to be 0, and output 2 is going to be 1. So therefore output 2 is going to be 1 again. And then it will go up, since output 2 is 1 again, and output 2's complement is going to be 0, and output 1 is going to be 0 again, and this will keep repeating itself, because output 2 is always going to be 1 after we set it in our first scan time. So let's go ahead and see this. I'll build a the program. I connect it to the PLC. I download it. And I say run. Okay. So at first we can see that output 1 was on for the first scan time, then it turned off immediately at the blink of an eye, and output 2 got the state of 1 and it keeps the same state forever, and therefore forever, or so long as the PLC program is run, output 1 is going to be 0. So this is how we can do this using internal relays. But we could achieve the same thing by using an input signal from an external device. So I'll go ahead and show you guys how that can be done. So we have our input, and then we have 2 outputs and 1 internal relay again. So when the input is 1, since output 2 is going to be 0 initially, output 2's complement is going to be a 1, and output 1 is going to be on. And when input 1 is 1, in the next rung, output 2 is going to turn into 1, which will make output 2's complement go to 0 in the next round. And no matter what the input is, in here, this is going to be 0. And since the input is not changed, and here output 2 is going to be 1 again, and it will keep repeating itself. So let's go ahead and show this as well. Again, the same steps: build, connect, and transfer. And now we can run it here. I need to force input 1 to 1. So as soon as I did that, output 1 was 1 for a split second, which is the scan time of our PLC program in here, and then it turned to 0 because output 2 turned into 1. In our 6th example, we are going to work on an oven system. So we have a heating oven, and it has 2 bays, and in each bay we can have a rod of, let's say, steel. So when the heater is on, it is able to provide enough heat for 2 of the rods, but in the condition of having only 1 rod, it is possible that the temperature becomes too hot. And when that happens, we are supposed to turn on the fan so the temperature goes below the set temperature, goes below the temperature which is supposedly too hot for the system. So it is okay if we have two rods in the system, but it is not okay if we have only one. So if we have two rods in the system, the fan is not going to be activated. It is going to be activated only if we have only one rod present, either in bay 1 or in bay 2. So that's one of the conditions. And another condition is temperature reaching a certain level, or passing a certain level. So we can have three inputs, one input each for each of the bays, to check if we have a steel present at one of the bays, and one input to see if the ambient temperature or the temperature in the oven has passed a certain level. So the condition of rods being present in one or the other bay and the temperature passing a certain level is going to be an AND relationship. So the temperature has to be higher than a certain level, and just like I say AND as I'm talking, that's what I should be doing in my programming. And in here I can also emphasize why I suggested during the last lecture that it will be a good idea to start writing down simple sentences before we start doing the hardcore programming. Then after we have written some simple sentences as to what is required from us or what is required from the system, then we can go ahead and translate those requirements into a graph set showing what the program should be doing in seconds. Then that can be put into a program. So in here the temperature has to pass a certain level, and we need to have a rod present in only one of the bays. So it should be when it is present in bay 1, then there should be nothing present in bay 2, and when something is present in bay 2, there should be nothing present in bay 1. So therefore we have this relationship in here. So this OR relationship between these two is going to show us that, okay, only one rod is present, so there is only something in one of the bays, and the temperature has passed a certain level, then okay, the fan should be on, and it will be on. So let's go ahead and build a project. Connect to the PLC. Say OK. Transfer it. And then run. So let's say we have a rod present in bay 1 only. Okay, so that fulfilled this first branch in here, but the temperature has still not passed a certain level because it is something that may or may not happen. Let's say it has happened. Okay, the fan is going to be on. But if we have a rod present in both of the bays, then we break the circuit and the fan is not going to be on. So that's how we can approach the 6th exercise. So the 7th exercise is a simple or logic, where we have to develop a program that will cause output D to be on when push button A is on or either B or C is on. So when either one of these 3 buttons is on, or when they are all on, or where any combination of them is on, then D is going to be on. So that's just going to be A or B or C. So we are going to have 3 inputs. They are going to be connected to each other in OR fashion, and we will have an output. I want to move on to exercise 8, which deals with a safety system for a car. So we are being asked to develop ladder logic for a car door seatbelt safety system. When the car door is open or the seatbelt is not done up, the ignition power must not be applied. If all is safe, then the key will start the engine. So we can see that there are going to be 3 inputs in the system. One of them is going to be related to the car being open or closed. The other one is going to be related to the seatbelt being done up or not. And the third one is going to be the ignition key. So if you have the key for the car, if you have the right key for the car, if the door is closed and the seatbelt is done up, then the ignition is going to be applied to the car. So let's go ahead and see how this can be handled. We are going to have 3 inputs as I said, and we define them in the very same way as we have been defining them. I named them car door, ignition, key, and seatbelt. Car door, key, and seatbelt, namely as the inputs, and ignition as the output. So let's go ahead and look at the program. So the car door has to be on, the car door has to be closed, and the seatbelt has to be done up, and we need to have the right ignition key. Then we can have the ignition. So as you can notice, when I'm talking I say and. So car door has to be on, and seatbelt has to be done up, and the ignition key has to be present. Then the engine can start. So these 3 inputs are going to be connected to each other in AND fashion. So that's how we can tackle exercise 8 in here. Let's go ahead and look at exercise 9. In exercise 9 we are supposed to design a motor controller, and that motor controller is going to have 2 buttons. One of them is going to be a forward button and the other one is going to be a reverse button. The motor forward and reverse outputs will only be on when one of the buttons is pushed. So when both of them are pushed, the motor will not work. So it can go either forward, it can go either forward or reverse, or it can stop. So when forward is active, reverse cannot be active, and when reverse is active, forward cannot be active. So let's go ahead and see how this one can be programmed. So we have button forward and button reverse as the inputs, and the machine can either go forward or reverse. So forward and reverse are going to be our outputs. When button forward is pressed, but not button reverse, then it goes forward. When button reverse is pressed, but not button forward, then it goes reverse. And when both of them are pressed, then it doesn't move anywhere. So let's go ahead and write what kind of truth table we are supposed to have. So we have, let's say, A here. I'll go ahead and write A, and then B, and then I have an output in here. So 0 0 0 1 1 0 1 1. So these are my options. So when none of them are pressed, the output is going to be 0. When one of them is pressed, the output is going to be 1, let's say. The other one is going to be pressed, the output is going to be 1 again, meaning that the motor is going to be moving. And both of them are pressed, the motor is not going to be moving. So the only way the motor is going to be moving is either when I have A prime B and A B prime. So in these two conditions, the motor moves. So A B prime, A prime B. But A prime B is related to motor being in reverse direction, and AB prime is related to motor rotating in the forward direction. So therefore we have A B prime for one state and A prime B for the other state. So that's how we can tackle exercise number 9. In our final exercise, number 10, we are going to try and design a simple alarm system for a house. So we have a burglar alarm, and this alarm works in the following way. When it is activated, the alarm and the lights will be activated to encourage the guests to leave. The alarm is going to be activated if an unauthorized intruder is detected by window sensor or motion detector. So we have two different sensors or detectors in the system. So the window sensor is effectively a loop of wire that is a piece of thin metal foil that encircles the window. So if the window is broken, the foil breaks, so the conduction is breaking as well. This behaves like a normally closed switch. So when the window is closed, so is the switch. And when it opens, the switch opens and it turns into state of 0. So in here we can see the inputs and outputs. So the window or door sensor, in this example, in our window sensing mechanism, when it gives a signal of 1, then it means everything is okay. Nobody has tried to come in through the window. And let's go ahead and talk about the motion detector. This motion detector is designed so that when a person is detected, the output will go on. So meaning that when there is nobody, then the output is 0. So it is okay. it means we don't need to be alarmed. But when it detects somebody, then the output is going to go to 1. So these are the two inputs in terms of sensors. And we will also have an additional input, which is going to be the activation switch. And we will denote it by S. So when it is 1, then the alarm is going to be active, the alarm system is going to be active. And when it is 0, then the alarm is going to be off. Yes. So let's go ahead and summarize what is supposed to happen. So first, if we want the alarm to be operational, then we need to set the activation switch, and when it is set, then the system will start checking or scanning the sensors. If the window or door sensor is broken, it gives the signal of 0. Then we are going to turn the sound and lights on. Or if the motion sensor is on, it detects some movement, then the sound and alarm are going to be on as well. And if both of them are detected, meaning that if the window or door is broken and the motion is sensed, they will also go on. What we need to do is to go ahead and set a truth table in here. So in this example, we are going to have a set switch, we are going to have a motion detector, and we are going to have a window sensor, and we are going to have an output, which is going to be the alarm. So let's go ahead and write down what can be happening. So we have 3 inputs. It means that we are able to have 2 to the power of 3, which is 8 different states in our system. The first one is going to be 0, 0, 0. The second one is going to be 0, 0, 1. The third one is going to be 0, 1, 0. The fourth one is going to be 0, 1, 1. The fifth one is going to be 1, 0, 0. The sixth one is going to be 1, 0, 1. The seventh one is going to be 1, 1, 0. And then the last one is going to be 1, 1, 1. So these are all the states that the system can have. Now we are going to examine under which conditions the alarm is going to be turned on. So in all these cases when the alarm is not set, the alarm will never go on. So the output is going to be 0. Then when the alarm is set, we need to examine the conditions of the sensors. So it is sufficient for any of the sensors to detect something for the alarm to go off. So it's in here we say when the window or door sensor is 1, it's okay, but when it is 0, then it means that the system is going to go off. So whenever we see that the W is 0, then it means something is not okay. So W is 0, then it is going to be 1. When we see W is 0, it is going to be 1. And then what about the motion sensor? When we see 0 for the motion sensor, it means no motion is detected. But when it is 1, it means some motion is detected. So in here, when M is 0, no motion is detected. So the output is 0. When it is 1, it means some motion is detected. So in these 3 conditions, the alarm is going to be off. So what are these? Those are S, M prime, B prime, plus S, M, V prime, plus S, S, M, and W. So these are the 3 conditions that the alarm is going to be on. Let's go ahead and see how we can make this simpler. As we can see that all these 3 expressions have S, so that is something common to all of them. So we can write it in here. So M, V prime plus, we are going to have M, V prime, and then we are going to have M, W in here. So that's what we have. So the first 2 terms in here, they have V prime as common. So what we can do is that we can put them in the parentheses of V prime, which is going to give us M prime plus M. Then we are going to have M, W. In here, M plus M prime is going to give us the result of 1. Therefore, our function in here, it turns into being SW plus M, S in parentheses W prime plus MW. So that's what we have. And there is a rule. So whenever we have A plus A prime B, that is equal to A plus B. So this in here is the rule. So if you make an analogy in here, in our case, W prime corresponds to A and M corresponds to B. So it means that our function is going to turn into being S W prime, which is A, plus M in here. So that is our function. So this is our function. So the alarm is going to be going off when it is set, and either the window is broken or some motion is detected. So it corresponds just right into the real life situation. So let's go ahead and have this function in mind and see the corresponding letter program. So we have three inputs: motion detector, window, and the activation switch. So the alarm has to be activated. S is in multiplication form to W prime or M. Let's go ahead and see what will happen in the program. We're connected to the PLC, it's okay, we downloaded to the PLC. So the window sensor, when it's not broken, is going to be 1, of course. And when we set the alarm, it's going to be set. Let's say we detect somebody and then the alarm goes off. Or we don't detect anybody, but the window is no longer closed, then the alarm is going to be active again. When we detect somebody and the window is no longer closed, the alarm is still going to be active. But no matter what the situation is, even if we get some detection from the sensors, if the alarm is not set, then it will never ever go off. So that's the end of this lecture. As always, if you have any questions, you are more than welcome to contact me in my email.